So I'm Arto, the other main organizer, but Luigi has been doing most of the work. So thank him for all the good things and me for all the bad things. So what I'm just going to say is talk a bit about what do we mean by probabilistic AI and why are we talking about it. So I'm not going to go into any technical details because we have a full week about those. But let's start with a very simple exercise. So you don't need TAs for this. So how does this sentence end? So maybe any of you shout an answer. What would be great? Any other options? Important, cool, short, fun. I hear fun. Okay, this is good. A lot of good choices. I also made my own guesses in advance that what you're going to say. I didn't pick up cool or great, but I did pick up fun. And I also kind of wanted to just kind of be extensive and think that you could be shouting anything, like summer schools are out of order is kind of grammatically properly valid sentence. But the important thing I actually wanted to say is that, I mean, there's the different probabilities associated with what you could have said here as an answer. So these are actually my own subjective estimates of what I thought you might be shouting, that there is 1 in 5 chance that one of you says fun. And you did. And I was quite sure that you're not going to say out of order, but it's definitely not impossible. One of you could have maybe seen my slides in advance and shout this. So I had to give some sort of a probability on that. Of course, now if I were to give the talk again, I would most likely update these probabilities. I would think that great is actually a great answer to this question. So maybe I should have it here on the list very early on. So when I talk about probabilistic AI, what I mean is that any AI method that we are ever going to develop should acknowledge a couple of basic things about how the reality works. If there is a problem, there's usually going to be multiple possible solutions. Like there were multiple possible continuations for this sentence. Importantly, some of them are likely and some of them are unlikely. So there's a difference in the probability of these things happening. And very critically, we don't actually know the probabilities, except maybe in special cases. In most cases, we don't. We just have our own estimates of them. I had 20% for fun. I maybe could have put a bit higher probability now that I heard one of you say that, and I certainly didn't attribute high enough probability for some of the obvious answers because I just couldn't think about them. So if I were to give this talk 100 times, I would probably get fairly good estimates of what certain types of audiences would shout. If I were to give the same talk in a kindergarten, I would probably need to change my probabilities quite a bit. And in practice, then, what an AI method needs to do, it needs to somehow represent and manipulate these probabilities and the uncertainty that we have about the world. Whenever we see new data, these methods need to somehow update the probabilities that we have. Otherwise, it's not really, we're not learning anything. It's not really an intelligent system if it's repeatedly making the same claim. And I would also say personally that no matter what kind of an AI we have, it should also communicate this uncertainty for the user or, let's say, another algorithm that is taking up the answers. So we already have a lot of good examples of this, like weather forecasts. They come with uncertainty estimates, at least the good ones come with those. So we know much more about the system if we are being told how uncertain the model is about certain things. Most of the time during this week, we are talking about machine learning. not of any kind of AI, but we are mostly talking about machine learning, to the extent that we might even have the name as probabilistic machine learning. But I do think that, most of the concepts are applicable to various techniques that you would not call machine learning. We would still need to worry about uncertainties. We would need to talk about communication of those. So we rather use the ProbAI. It's also a funnier acronym than ProbML. Also, one thing that I think is a very important thing to remember is that, we've known, we as the humankind, we've known for a very long time how to operate with probabilities. And there's the kind of whole field of probabilistic calculus or statistics that worries about this. So we, of course, build on that. We would never, ever think of replacing something that is essentially mathematically proven or a very reasonable set of axioms. But we do differ from statistics in a very broad sense, that we are talking here about mostly fairly general purpose models, methods that are intended to be applicable in different domains, different types of problems. And we worry a lot about computational practicality. Well, you could do theory on these things also, but we are talking about, we have practical exercises in many of the lectures, and we really want to kind of learn how to do something in practice. But okay, this is like a very, very high level, almost like redefinition of the concepts. But let's talk about then a bit about machine learning and why do we really need to worry about probabilities or being probabilistic in these things. So this is something that I presume, based on the tight selection of applicants we went through, that you are more or less familiar with this one. So this is a simple example of a supervised machine learning process, one particular type of formulating it. So what we usually do is that we assume that we are given data, some pairs of inputs and outputs, X and Y, that are sampled from some unknown probability distribution. If we knew the distribution, things would mostly be kind of easy. And what we're then doing is that we are fitting a model. Could be linear regression, it could be a deep neural network, it could be any model, but usually, in the simplest case at least, it's a parametric function from the inputs to the outputs, and it has some parameters theta. And the choice of the theta depends on how the function in reality behaves. And then what we do is that we solve an optimization problem. We have some sort of a loss, maybe some sort of a regularizer there. No, it doesn't matter actually at this point that what is our objective, but we simply have some collection of training data, some examples we've drawn from the distribution, and then we want to minimize this loss with respect to the parameters, and then we get our solution, a theta hat. This is like the textbook 101 definition of supervised machine learning, that this is the first encounter to machine learning for most of the people. And the important thing about machine learning, why do we need machine learning, and why standard simple optimization is not solving our problems completely, is that we don't actually care that much how well does our function work on this particular training data we have, but we care about the generalization ability. So how well does it work on future samples, future inputs X that come from the exact same distribution? In the simplest case, in more complex problems, you would maybe allow the distribution itself to change as well, but let's not worry about that yet. Generalization is easy if you have infinite data. Literally infinite. So not just a large number, but you really have as much as data, so that you can simply essentially estimate your probability, the unknown probability distribution perfectly. Then it's fairly easy, not trivial, but it's fairly easy to find a solution that also generalizes for new instances. But this is, of course, never the case. We simply don't have infinite data. So given some sort of a finite collection, doesn't matter whether it's 100, 1,000, or 1 billion data instances, what we need to worry about in machine learning is that how do we achieve good generalization conditional on only having whatever data we've recorded. And this is where the uncertainty or the probabilistic treatment of AI machine learning comes into play. So here is a simple problem, a one-dimensional regression problem. So the horizontal axis is the input and the vertical one is the output. So there's an X and Y pair, some sort of a relatively smooth, simple function. And I'm showing here 1,000 data points drawn from the probability distribution, the unknown distribution. And I've already fitted a solution here. So the red line is my model. I picked a family of models, third order polynomial functions, if I remember correctly. And I just solved a certain loss minimization problem to figure out that this is my solution. Looks fairly good. It's not perfect. So the data doesn't actually follow my assumed model family, but I would say that it's a good enough description of what's going on here. But this is kind of relatively much data for an extremely simple problem. It really is a one-dimensional mapping from X to Y. And the problem is that when we have little data, so here I've assumed that I've only made 10 observations, the red dots here. And I again solve my same optimization problem. I'll get this fit that is still fairly good. I mean, this is so simple problem, one-dimensional problem. I can fit a model already with 10 data points. And it's not actually much worse than the one on the left. But the important thing is that it's not deterministic. It's not clear what the solution is. So here's another example. I picked another set of 10 observations, now with green dots there, and again solved the same optimization problem. I have a solution that is, again, a fairly good fit, but it's different. Now, the good question is, which one of these is right? And there's, of course, no right answer to that. Neither of them is right. They are different solutions to the same problem, obtained. They differ simply by the virtue that we had different data to fit this problem there. There's no magic in these two examples. So what I can do is that I can just repeat the same process lots of times. I'm not drawing the dots here, but I'm always just picking 10 samples from the same distribution and fitting a model there. And this is the set of all solutions I get for my standard supervised machine learning problem. They are all reasonably good. Some of them are starting to be a bit problematic. Here some tails that are not really reasonable. I think these are happening because in one of those sets, you didn't have any observations from this right-hand tail. And this is really the kind of crucial point here, that if you have fairly little data, then you simply cannot tell, given that data, that what would be the right solution, but there is some uncertainty on what the result might be. The problem here is that to achieve this understanding of how much uncertainty there is in my result, I had to cheat. I had to repeatedly take 10 new samples. And then by repeating that a lot of times, I was able to get a nice illustration of how uncertain we are about what the function might be. But now the real question is that we can't do this in most cases. If I am able to repeatedly take 10 samples, I can just as well find this solution on the left. I can just keep on pooling my data points, and then I have a large data, and there's no problem. The real problem is that how do we actually understand how much uncertainty there is in these results without cheating? So if I only really have 10 observations, then how do I figure out how well do we know this function? And this is, of course, where the statistical reasoning and Bayesian machine learning approaches come into play. I trust that you all actually kind of are aware of these basic concepts because of the prerequisites that we assumed. But this is kind of how I want to summarize what's the real important thing is. That at the point where we have any finite data collection, we should stop immediately thinking about finding a best possible parameter value. Instead, we need to acknowledge that our result is necessarily a probability distribution over possible parameter values. It might be a very narrow probability distribution if we have lots and lots and lots of data, but in most cases, it is not. And this is what it means to really actually do learning. We would need to figure out what are the possible solutions to this problem, how likely they are relative to each other. And we should learn to operate on this kind of concepts. And we do know the solution. We do know the solution to this. It really is the kind of standard Bayes rule. So I'm not going into any details on this. I think it's going to be covered on most of the lectures on some level. But the basic idea that we can start with an assumed model, some vague initial ideas of what we believe the parameters might be, and then we can use standard rules of probabilistic calculus to figure out what is the distribution of possible parameter values. Once we know this, we also need to use our models in a slightly different way. You cannot just feed your data to a model with some particular value for the parameters, but you need to consider in your prediction phase all the possible models that could have been true. So essentially, you will need to integrate over this distribution of possible values. Let's not worry about how do we compute these things yet, but just kind of assume that this is how we need to work. Here I'm directly jumping to a solution. So on the right, I have the same plot that I showed earlier. My quantification of how uncertain I am about the function if I only have 10 data points. But for that, I needed to really cheat and repeatedly get a new set of 10 data points. On the left, I have the right solution for this problem. So I'm only picking up these 10 data points, and I'm figuring out, based on the Bayes rule, what is the distribution of possible functions that would be compatible with these 10 data points. It's an interesting thing to compare these two things. So the first observation that I would make is that they are characterizing the uncertainty that we have about the function in approximately the same way. If you just glance at these very quickly, if you show these to a lay person who doesn't know anything about functions, they would say, yeah, they are the same. They're of course not exactly the same, and neither they should be. So we don't have this wacky results here, and we actually have here fairly high confidence that the function will turn kind of down at this end. This is correct. I mean, this really is conditional on this very specific set of 10 observations. It still does give you some probability that it would be going up here. So they shouldn't be the same, but we are getting the same overall impression. And here we just don't need to do any sort of cheating, and we only need the 10 observations. So this is pretty much what I mean when I talk about probabilistic approaches to AI. An important observation here is that we usually need to do this, almost always. I mean, you might have the kind of basic idea that Bayesian machine learning is something you need when you have very, very small data sets. Maybe you have only a couple of patients from having a very rare disease and you can't get more of those and so on. But it actually is not really true. So you would ideally want to do this always. So here's the uncertainty when we have made 10 observations. Here's it with 40 observations. Here with 200. We still have some uncertainty of what the function might be. And it's good to remember that this is one-dimensional problem. This is something that you can take a look at this point cloud and you can draw a line and it's immediately solved. Now, if you had, let's say, a deep neural network with 1 billion parameters or whatever the biggest transform models nowadays have, no matter how much data you have, we're still going to be unsure of the parameters. We're still going to be unsure of what the predictions are. So this issue actually never goes away. We still have uncertainty in the models and hence in the predictions, no matter how much data we have. All of this is broadly applicable, of course. So as long as we express our models in the right way, as accepting that all the parameters, all the unknown quantities are random variables, that we don't really know them for sure, then we can always, in principle, compute the posterior distribution. And it also, what's happening? My laptop just crashed, meaning that I would expect that I ran out of battery because the charger is not actually doing anything. Because the charger is not connected, that actually might explain the reasons. Let's see if I can get booted up. If not, I'll just continue anyway. Oh, this is good. Yeah, I knew my battery was running out. I did bring the charger, but I forgot to connect it to the laptop. Luigi, you are probably the only person that actually has my slides, a slightly older version of those, but it doesn't matter. If you are able to open it while, let's see. Now it is starting. Yes. It is working, but I'm probably. Let's do so that I don't try to join Zoom now. So we'll just have the Zoom session for a while. It takes a while if I would need to restart my browser and whatnot. The important thing here is that we can always solve this problem. And once we've solved the problem, once we have the distribution of the possible choices that we could have for the parameters, it has all the information we need for making optimal predictions, optimal decisions by integrating out over the distribution. The challenge is that computational. Most of the time, we cannot really compute the distribution in closed form in exactly, but we need to approximate it somehow. Most of the summer school is actually about some sort of computationally tractable approximations for the problem that I just talked about in different contexts. I'm of course not going to go through them now because you have a full week to learn about them, but I'll just give a conceptual illustration. So assume here that this is our true two-dimensional distribution of possible values for some particular parameters. That's our true posterior distribution. So we have plenty of ways of approximating that. One that you've most likely heard of is the Markov chain Monte Carlo. So a family of methods that approximate the posterior by drawing samples from it. So they essentially turn it to a finite collection of possible parameter values. We don't really talk too much about those on this summer school, but maybe that's them at some points. We do talk a lot about so-called distributional approximations, in particular variational approximation, variational autoencoder, and methods like this that simply postulate that, okay, We don't know what our posterior is, but let's assume that it's some simple parametric function, let's say a normal distribution. And then we optimize. We tune the parameters of this approximation so that it looks as close to the posterior as it can be. We also talk about, so let's say, slightly more modern ways of doing this. So ways of trying to learn more flexible approximations by using elements that we've in recent years learned how to use effectively, such as like deep neural networks, automatic differentiation, and so on. So for example, this is like a schematic illustration of something called a normalizing flow, where you would just take some very, very simple distribution and you push a distribution itself through a neural network in order to parameterize a very flexible distribution. And that can be used for approximating the posterior. Skipping here, of course, all the details. But this is the kind of realm where we largely work. So we talk about ways of trying to approximate this computationally challenging problem of figuring out what do we really know about our functions. No matter how we did it, we can still solve our actual decision problems like learning a classifier or something. The results are not going to be the same because we made some error in making this approximation, but they're all usually going to be good enough. So that's the basic story. This is roughly what the school is about. I'll just conclude with some very, very simple examples on where these kind of techniques are being used. First of all, for example, Gaussian processes, we have one talk about those. It's actually like the proper way of solving this 1D regression problem that I was showing, which actually allows you to quantify the uncertainty, not as uniformly kind of in every location, but you get different kind of uncertainty. You are more certain of the function closer to the observations. There's a lot of matrix factorization techniques that are inherently building on Bayesian machine learning. For example, many of the recommender engine techniques that we've been used for a very long time. And nowadays, a lot of modeling is done with something called probabilistic programming, which is essentially hiding the computation from you. It's just asking you to specify your model and saying that, okay, let's use an inference engine that knows how to do the reasoning. These are the kind of simple examples that you often see. But I would like to maybe highlight some examples of how this probabilistic reasoning is, probabilistic methods are at the core of also many of the large scale complex problems that we are today being solved. This is already a couple of years old, one practical example of variational autoencoders that we will be covering here, being used for image generation, these kind of typical high profile applications of AI. Another example from one of our lecturers that is about how do you do Bayesian inference in context of differential equations that are, of course, underneath many of the applications, for example, in natural sciences. So there's plenty of uses for the techniques that you'll be learning about in various domains that are not immediately kind of classified as typical Bayesian machine learning models. So final slide before we enter this break where you get to still register for the Unity event. I just remind about my own personal opinions of what probabilistic AI means. So AI, no matter what AI, it must account for uncertainty in some way. It has to do it correctly. So we know already standard rules of probabilistic calculus. We must kind of obey those. We must formulate our models in a way that allows us to build on this knowledge. And whenever we finally have learned how much we are unsure of what the model needs to be, we should always integrate over this uncertainty while we are making predictions. We cannot forget it at some point. We need to communicate for the user. We need to take it into account when making predictions. And the fundamental problem in many of these approaches is that this is computationally challenging. The theoretical derivation is very easy, it's very general, holds almost always. The question is, how and when can we do this in practice? And how do we do it efficiently? What are the limitations? What do we need to do in each of the cases? On this summer school, we talk a lot about variational approximation as one prototypical family of computationally efficient solutions for the posterior inference. But we also cover, especially towards the end of the course, many of the kind of modern techniques where we get more kind of expressive, more flexible approximations by building on everything that is happening in the AI research community during the last 5 to 10 years. You won't be a master of all of these topics at the end of this week. Life would be very easy if you could leave it, learn it in 1 week. But you will have the background of working in the field, following it, building on it. And then, of course, you focus on your own things, or then you forget everything about probabilistic AI after this week. I hope not. Thanks. So that's everything from now. And we'll continue at 10. So now there is this few minutes time to go and just fill in your choice for the Unity event. I think this is the most important thing for now.